Okay, so we'll be continuing on our discussion on vectors and vector algebra. So next on our discussion would be the operations on vectors. So let's discuss first the discussion on the operations on vectors. Okay, so here the basic idea or the basic concept for the vector algebra is that scalar quantities can be added, it can be subtracted. Quantities can be multiplied together by ordinary arithmetic, but vectors, however, requires different technique or additional techniques in order for them to be added, subtracted, or be multiplied. Of course, the difference between the operations on vectors and between vectors and scalars is that the description for vectors requires we consider the uh, direction associated with vectors. If the quantities are simply scalars, we add them, we subtract them, we multiply them together using ordinary arithmetic, such as, for example, when we add 2 kilos of rice with 3 kilos of rice, you end up with 5 kilos of rice. So what we have done in this example is we just simply add them together using ordinary addition. The same goes with subtraction. For example, when you subtract 5 kilos from 8 kilos, you would end up with 3 kilos. Uh, Multiplication also for scalars, you are only required to do ordinary multiplication, such as when you are asked to get the area of a given space, you just multiply length times width, so you end up with the ordinary multiplication for scalar quantities. However, for vectors, you need to consider the specification of the direction of that vector in before you add them together, or before you subtract or you multiply the vectors. The analytic method is also called the methods of component, and this is the method that we will be discussing later on when we do vector addition. Okay, so before we do the actual analytic method or the graphical method, we first discuss the resolution of vectors. Now, this is the basic requirement to do the vector addition or vector algebra. To add vectors, each given vector must be resolved first into its corresponding components. One along the x-axis and one along the y-axis of the Cartesian coordinate system. Each component is determined by solution to right triangles by trigonometric function, whether you make use of sine or cosine. So sine or cosine only. I assume that since you are taking physics 1, either that you are taking your trigonometry, or you have taken your trigonometry from your previous semester. It is very important that you review the solutions to right triangles for trigonometric functions, since this is the main mathematics that we will be employing in order to resolve components according to its resolve vectors according to its components. Okay, so take note that each resolved component of a vector follows the sign of ordered pairs in the Cartesian plane according to quadrants, such as what we have discussed previously in the previous video. That on the first quadrant you have positive x, positive y. Therefore, if a vector is located on the first quadrant, its components would be positive x and positive y also, and so on for the succeeding quadrants. Anyway, we will be discussing more on that in detail when we do examples. Okay, so vector addition. Vector addition is done by adding the corresponding components of a vector according to axes. So the main idea here is first that we resolve vectors according to components before we add them together. and the vector addition is actually performed according to the addition according to components based on its axis, meaning you add only x with x, you add y with y. The sum of the vectors is called the resultant vector. Add all x components, the sum of all x in the is the resulting sum of all the components of the vectors in x would be the component of the resultant vector in x. When you add all the components in y, the sum of all y components would be the component of the resultant vector in y. Now, in vector addition, take note that the signs of the corresponding sums of the components lead to the quadrant where the resultant vector lies. So that means, for example, if you have the sum of the vectors in your component x, such as located here, if this results, for example, to a positive number, if your y component results into a positive number also, that means that your resultant vector is expected to be located on the first quadrant, since on the first quadrant the component of x is positive and the component of y is also positive. Now, for example, the resulting sum would be, for example, this sum is negative x and this is also negative y, then this is negative negative, then that means your resultant vector would be on the third quadrant. Later on, we will be detailing this idea using examples. Okay, so vector subtraction. So vector subtraction is simply vector addition, but this time with negative vectors. So for example, if you are given vector A and vector B, vector addition would be A plus B, whereas vector subtraction would be A minus B, wherein A minus B is simply the vector addition of A with the negative vector of B. Okay, so how do we solve for the magnitude of the resultant vector? The magnitude of the resultant vector is simply computed using Pythagorean theorem. If you recall the Pythagorean theorem states that the square of the hypotenuse is equal to the squares of the individual legs of your right triangle. So, for example, the individual leg is represented by your r sub x and your r sub y. You square r sub x, you add that with the square of r sub y, then this results to the square of the resulting hypotenuse, which is your magnitude of the resultant vector. You take the square root of each to get the magnitude of your resultant vector. Now, of course, what is meant by this equation is that the sum of x is your r sub x, the sum of y is your r sub y. Now, to get the direction of the resultant vector, as we know that vectors, the complete description of any given vector, the same goes with the resultant vector, is you need to specify its magnitude, and the magnitude according to this is computed using Pythagorean theorem, whereas the direction is specified by the inverse tangent function, or the arctangent function. So the inverse tangent function is simply computed using summation of y over summation of x. Now take note that the resulting angle from the arctangent function is always an angle measured from x. Whenever we make use of this formula, inverse tangents, summation of y over summation of x, the summation of y is always on the numerator of this fraction. We expect that when we employ the solution for inverse tangent function, wherein y is on the numerator and x is on the denominator, the resulting angle would be always an angle measured from x. Thus, if the resultant vector is determined to lie in a given quadrant, the accompanying compass direction for the angle will be one of the following. It's either the angle would be north of east, north of west, south of east, or south of west, depending on which quadrant would be the resultant vector would lie. If the resultant vector would lie on the first quadrant, the associated direction for the angle as we compute for the inverse tangent function would be north of east. Now, if the vector would lie on the second quadrant, it would be the angle would be north of west. On the third quadrant, it would be south of east, and on the fourth quadrant, it would be south of west. Now, the resultant vector, just like any other vector, is written in the form magnitude plus direction. The direction is should be written in the form of the angle plus the compass direction. Or in symbols, this would be your r is equal to the magnitude of r and the accompanying angle with compass direction. Okay, so let's go back with, let's do some examples. Let's start with problem number 1 that we have presented before, or we have made use before. Remember our problem number 1, a car drives 50 meters towards the east, then stopped by a red light at a crossing. After the light went green, the car drives another 82 meters towards the same direction. So the question is, what is the car's resultant displacement? Okay, so what we see in the table here is the description of the given vectors, but this time with the accompanying solution for the resultant vector. Now, our first vector is 50 meters. It is directed towards the east direction. Its accompanying angles would be 0 degrees. Our second vector is 82 meters towards the same direction as specified in the given problem. So therefore, they have the same direction, east, and they have the same angle, 0 degrees. Now, as presented in the discussion previously, the first step in doing vector addition is that you need to resolve the given vector according to components. So you have the components here, x and y component. Now let us define first the x component. The x component, as you can see here, is the projection of a given vector on the x-axis of the Cartesian coordinate system, while the y component is the projection of the vector on the y-axis of the Cartesian coordinate system. Now let's try to do some drawings for this vector. Let's do the graphical method. Before we proceed with the given problem, let us try to first discuss the concept for the graphical method. Okay, so this is the main idea. The resultant vector can be determined graphically by drawing the given vectors in the Cartesian plane. When drawing the given vectors in the Cartesian plane, we need to draw these vectors according to scale. Remember that the length of the vector arrow represents the magnitude of the vector. So that means if you draw two vectors, one is longer than the other. Therefore, the longer vector or the longer arrow should represent the larger vector in terms of magnitude, while the direction of the vector arrow is specified by its angle. Vectors can be drawn in the Cartesian plane and determine the resultant vector by any of the following methods: drawing the given vectors from the origin, using the parallelogram method, or using the head-to-tail method. Each of these methods will be described later on. Now, drawing vectors. The graphical method for determining the resultant vector uses appropriate scale ratios to represent actual unit of scale to scales used when drawing the vectors. So for example, when you do your own drawing, you would not actually draw 1 kilometer in your paper. What you need to do is, for example, to represent 1 unit of measure in your paper, to represent, for example, 1 kilometer. So for example, that ratio of 1 unit in your paper to 1 kilometer of your given vector uses the ratio 1:1. Now, so for example, in this Cartesian plane of drawing, this particular length of unit specified in this scale, you have 1:1, 1:10. So for every 1 unit in the scale. This is 1 unit. This is 1 unit. This represents 10 units of scale in the actual representation of the vector. So for example, this is expressed in kilometers. Then the scale specified as 1 is to 10 represents 1 unit of the scale in the given graph is to 10 kilometers representation of the actual length of the given vectors. Of course, the idea is that you cannot actually draw 10 kilometers in the Cartesian plane, but you could only congest the 10 kilometers by representing it using proper representation of scale. Remember that the length of the vector arrows when drawn must be in accord to the set scale. The direction of the vector arrows is measured using a protractor. So, of course, meaning if you draw vectors, you make use of for example, graphing paper or simply any plain paper. You draw your Cartesian. You draw the length of the vector arrow using rulers, and for the specification of the direction, you make use of a protractor. Now, to add vectors graphically, each given vector must be resolved into components, just like what is just like what we have discussed in the analytic method. But of course, in the analytic method, we are doing the resolution of vectors analytically or mathematically. The components would be of the given vectors would be one along the x and one along the y-axis of the Cartesian coordinate system. Each component is determined by solution of right triangles by trigonometric functions to specify the value of the length of the arrows. Each vector drawn from the origin will have its projection along the axis. These projections are the components of the given vectors. Now let's try to have an example of a drawing for the vector addition. Let's try to draw first the arrows, drawing the arrows from the origin. Now, so as you can see, we have actually 4 vectors here. As specified in this table, we have the following vectors. We have d sub o, we have d sub 1, we have d sub 2, we have d sub 3, and finally we have r. Of course, d sub o is represented as the blue vector arrow. You cannot see the blue vector arrow here because of the idea the given vector arrow is 0 in magnitude, therefore it has no length. But d sub 1 here has the color green. That means the vector arrow would be this one. Try to notice that the entire vector is projected along the y-axis. Why is that? It is because that the entirety of the vector arrow specified in its description, the direction of the arrow is directed west. Therefore, the angle would be 180 degrees, and therefore, the vector arrow should be drawn entirely on the negative x-axis. Okay, so d sub 2. D sub 2 is colored purple, so its vector arrow is this one. It is on the first quadrant, as specified here. The direction of the vector arrow is east of north. East of north is, of course, is measured from the y-axis. East of north meaning north going towards the east, so that means north. Measuring the 45-degree angle towards this direction, east of north. The angle is 45 degrees. Okay, the next vector is vector d sub 3. It is colored orange. So the direction is east of south. This is the vector. East of south is this direction. This is the 60-degree angle. This is a 30-degree angle. So therefore, the direction east of south is this measure. And finally, the red arrow here is the resultant vector drawn graphically. Take note that the resultant vector is directed north of east, 80.16 degrees based on the computation here. 80 degrees, 80.16 degrees north of east. That means that the angle is measured from the positive x directed towards the counterclockwise direction, this is your 80.16 degrees angle. Okay, so let us try to show the components of the of the given vectors. Try to look at the following projections. Each of these projections as represented by the dashed lines and the shadow projections on the x-axis and on the y-axis, these are actually the length of the vector arrows represented uh, by this computation of the x and y components. Take note, for example, for our green vector or our vector d1, since our vector d1 is entirely projected on the west direction, the west direction is the negative x direction. Therefore, the entirety of the 210 meters should be projected on the negative x-axis. And the component would be negative 210. It has no y component since the entirety of the vector is on the x-axis. Therefore, the y component of this vector is 0. Now take note that we have written here that the vector component for the west direction 210 should be specified as negative. Since the idea is that it is directed to the west, that the west direction is negative x, this negative sense of the direction is specified by assigning the negative sign on our component. So negative 210. We will be doing this idea of assigning signs in all the components accordingly based on the location of the given vector. Our purple vector d sub 2 is on the first quadrant. Therefore, its projections should be both positive since on the first quadrant x is positive and y is also positive. Take note of the length of the vector arrow. The projection of the vector arrow, this is drawn almost at 125, just like specified here, 127.28. The vector is actually drawn a little above 125. Take note that the scale that we are using is 1:25 meters. So that means for every unit here, this single unit represents 25 meters in the actual length of the vector. The angle is 45 degrees. Therefore, the length in the x of the length of the x component and the y component are the same. And finally, for the orange vector or our d sub 3 vector, the direction is east of south, 60 degrees east of south. Therefore, our vector is located on the fourth quadrant. On the fourth quadrant, the x component would be positive, and the y component would be negative. Okay, just like what we see in the vector diagram here. Of course, between the x component and the y component is the shorter leg of the vector, and the longer leg would be the x component. Just as we can see in the drawing of the vector, the y-axis is the shorter leg, and the x-axis would be the longer leg. Now, how do we specify the sum of the vectors? Simply, the sum of the vectors is the sum of the x components or all the components. We ended up with 12.54 because we add the following values: negative 200. We add that with 127.28. We add that with 95.26. We should end up with 12.54. You should verify this using your own calculators. The same goes with 72.28. We ended up with 72.28 by adding up 127.28 minus 55. Of course, when we do the computation for the Pythagorean theorem, so that we could combine r sub x with r sub y to form our overall vector, we make use of the Pythagorean theorem. We should end up with 73.36. You should also verify this using your own computations. Now, how did we compute for 80.16? We make use of inverse tangent. we will be I will be presenting to you the solution later on, but at the moment we only specify for this module. I am just showing to you the vector drawings of these vectors. Okay, so let's proceed. The vector addition is done by adding the corresponding components. Graphically, this is done by adding the lengths of the vector arrows representing the components of the given vectors by axis. This then results to two vectors on each axis, which are the components of the resultant vector. Combining these two vectors by parallelogram method determines the vector arrow of the resultant vector. So therefore, we need to, the idea is that we need to first discuss the parallelogram method. Okay, so the parallelogram method. The parallelogram method is the graphical technique of determining the resultant vector for two vectors at a time. The method describes that the given two vectors are drawn from a common point and then drawing the shadow projections of each other's vector's tip, forming a parallelogram. The resultant vector is the vector drawn from the vertex of the two vectors to the vertex of the two shadow projections. So let's take have an example, parallelogram method. Now, as described in the concept, the idea of the parallelogram is that you draw the two vectors on a common vertex, such as the location of the origin. So in this given set, we have the blue vector as vector A, the green vector as vector B, and again, the red vector is our resultant vector. Now, the first vector, the blue vector, vector A, is 45 degrees south of east. South of east is located on the third quadrant. So as you can see, on the fourth quadrant, south of east. As you can see here, that the blue vector, the first vector, is located on the fourth quadrant. Now the second vector, the green vector, is vector B. It is measured 37 degrees south of west. So south of west is on the third quadrant. So you can see here that the vector here is drawn on the third quadrant. Now, the idea of the parallelogram method, once you have drawn the two vectors on a common point, such as the origin, what you need to do is to draw the corresponding vector shadows of each vector on the tip of each of the given vectors. So for example, the projection of the green vector, which is this one, was drawn from the tip of the first vector. The projection of the second vector, which is the blue dashed line, was drawn on the tip of the green vector. So each of these two projections would intersect at this point. Now, to draw the resultant vector, the resultant vector simply is the vector drawn from the vertex of the two tails of the two vectors, pointing towards the vertex of the shadow projections of the two vectors. Now, the parallelogram the method comes from the idea that when you do this process, you will be forming this parallelogram. Okay, next, the head-to-tail method. The head-to-tail method is a graphical technique for determining the resultant vector by drawing the given vectors head to tail. Head to tail in succession instead of drawing the given vectors from the origin or from a common vertex. This method can be used for determining the resultant vector for any given number of vectors, not unlike the parallelogram method that the parallelogram method is only used two vectors at a time. The head-to-tail method, you can use this method for any given number of vectors, two or more. The resultant vector is the vector drawn from the tail of the first vector to the head of the last vector. So let us illustrate that. Head to tail. Okay, so let's describe first the set of vectors. We have the blue vector d sub 1, we have the green vector d sub 2, we have the purple vector d sub 3, and finally, again, the red vector as the resultant vector. The magnitudes are the following: 72.4 meters, 57.3 meters, 17.8 meters. Our corresponding angle measurement is 32 degrees east of north. So the location of the east of north direction is on the first quadrant, just like as we have drawn here that the blue vector is located on the first quadrant. The green vector or d sub 2 vector is 36 degrees south of west. South of west should be on the third quadrant. Now we cannot see directly here since we have drawn the vector head to tail. But if we're going to draw the vector from the origin, we can see that the vector is located on the third quadrant. Okay, so the purple vector is directed 270 degrees directly on the south direction. So that means that the vector arrow, the purple vector, should be directed towards the southward direction. And again, we cannot see directly here except that the purple vector is directed towards the downward direction. But if we're going to draw the vectors from the origin, we can see that the vectors from the origin is directly drawn on the negative y-axis, since the south direction is on the negative y. Now, the corresponding components should be computed accordingly using sine and cosine. We haven't discussed this yet, but we will be discussing this on detail when we do the analytic method. But at the moment, let us be it would suffice to say that if we have computed accordingly the components, this would be the corresponding components. This would be 38.37. This is positive for both of the components x and y for the blue vector, since the blue vector is on the first quadrant. The second vector is the green vector is directed towards the south of west direction. This is on the third quadrant. Therefore, the corresponding components would be both negative. And the third vector, the purple vector, is directed towards the south direction. Therefore, the entirety of the vector is on the negative y-axis. So we have the entirety of the 17.8 meters should be on the y-axis only. You have a zero component for x. Now, drawing that head to tail, we will be having this diagram. Now, how do we determine the resultant vector? Graphically, the resultant vector is the vector drawn from the tail of the first vector to the head of the last vector. This is your first vector. This is your last vector. The resultant vector is the vector drawn from the tail of the first vector here, ending up with the head of the last vector. So this is your red vector, or the resultant vector drawn from the tail of the first vector ending up to the head of the last vector. So that is the method for head to tail method. Now let's do the corresponding examples for that we have previously presented, problems number 1 up to problem number 4. Let's start with problem number 1. Okay, so this is the original set of the vectors. So we have assigned that the x sub 1 vector, or the first vector, is the blue vector. The second vector would be the green vector. If we're going to draw this from the origin, we will have this diagram. Now, take note, just like as we have presented here as an error, we should adjust the scale accordingly. So, for example, if we make use of, for example, 25, you can see that we have a check here. That means that the scale for the to be used is correct. Correct in a sense that it could accommodate the length of the arrows when we draw the vectors. So when you do the same drawing in your own drawings of the vector, you should also include such condition as specifying the scale of the vector so that it could include the length of the vector when you draw them on your own on your paper. Okay, so let's draw the vectors from the origin. So as we can see that the blue vector is this one. It was overlapped by the red vector. The red vector is actually your resultant vector. The green vector, as drawn from the origin, is directed towards this direction. Both of these two directions is pointing towards the positive x direction, since both of the two vectors is pointing towards the east direction. If we're going to draw the two vectors head to tail, let us first delete the two vectors. Let us draw this head to tail. Try to notice that the green vector is somewhat missing, but it is actually underneath the red vector, because the green vector is actually drawn from the tip of the first vector, the blue vector, ending up at this end, so that when we draw the resultant vector, remember the resultant vector is the vector drawn from the tail of the first vector ending up to the head of the second vector, or the last vector. So meaning the red vector should be drawn from the origin up to the tip of the green vector. Of course, the resultant vector, which is 132 meters, should be the length of this arrow. Okay, so let's have example number 2. Problem number 2, a student walks 10 meters towards the east, then realized that he had dropped his notebook behind him and walks back a distance of 6 meters. What is his resultant displacement? Okay, so the given vectors, again, we have assigned the blue vector as the first vector, the green vector as the second vector, and the red vector as the resultant vector. Let us draw the two vectors from the origin. Okay, so let's set up the scales accordingly. Okay, so let's have this as 1. Our scale is 1:1 meter. Let us draw the two vectors from the origin. So as you can see, here you have 10 meters towards the east. This is the 10 meters towards the east, the blue vector. It is drawn from the origin. We cannot see the rest of the vector since the overlap of the resultant vector is covers the rest of the vector. The green vector, however, is directed towards the west direction, so that is 180 degrees, 6 meters. So this is your green vector, the second vector. Now, of course, the resultant vector would come from the difference of the components, but since the components is directed only on the x-axis, so you will only have 10 minus 6 resulting to 4 as your resultant vector. You have 0 components for the y, and the result would be positive. That means that the 4 meters component of r should be on the east direction as shown here in the given diagram. 4 units. If we're going to draw this head to tail, we will have the following drawings of the vector head to tail. Okay, so just like what we have specified in the idea of the head to tail method, you draw the two vectors in succession. You draw first the blue vector. So the blue vector is from the origin ending up at 10 meters. You draw the second vector head to tail, meaning the second vector, the green vector, should be drawn from the tip of the first vector, going towards the left direction for 6 units. This is 1, 2, 3, 4, 5, 6 units. Now the resultant vector is determined by drawing the vector from the tail of the first vector ending up to the tip of the second vector, or the last vector. Now the length of the vector is again 4 units for the resultant vector. 4 units, 4 meters. Now let's do example number 3. Okay, so example number 3, a car travels 4 kilometers north and then 3 kilometers east. How far and in what direction is the car from the starting point? What are the magnitude and direction of the car's resultant displacement? Okay, so let's draw the two vectors from the origin. Let us remove first the previous vectors. Let us draw this from the origin. Okay, so try to notice that this time each of the vectors is on different axes. Our first vector, the blue vector, is on the north direction, therefore it is on the y axis here. The second vector, the green vector, is on the east direction, so it is on the positive x-axis. Now, the red vector is actually the combined effect of the blue vector and the green vector, or the first or the second vector. How did we come up with this red vector? If we're going to make use of the head-to-tail method, notice that simply the head-to-tail method, you need to draw the first vector. You draw the second vector from the tip of the first vector, and the resultant vector is the vector drawn from the tail of the first vector ending up to the tip of the last vector. So therefore, even though that we cannot see the resultant vector from drawing the vectors head to tail, drawing the vectors from the origin, we can see the resultant vector if we draw the vectors head to tail. Now, since we only have two vectors, we can actually employ the parallelogram method to come up with the same resultant vector. Doing the parallelogram, try to notice that this is our parallelogram, but this time, since the two vectors are on the axis, our parallelogram is actually a rectangle. Now recall the parallelogram method. The parallelogram method is that you need to draw the two vectors from a common vertex, such as the origin. You need to draw the corresponding projections of each vector on the tip of each of the opposite vectors. So the projection of the green vector here was drawn from the tip of the first vector. The projection of the blue vector is drawn from the tip of the green vector, forming this parallelogram. Now again, the resultant vector using the parallelogram method is the vector arrow drawn from the vertex of the two vectors, pointing towards the vertex of the intersection of the two projections. Now let's try to have the fourth example. A postal employee drives a delivery truck along the route 2.6 kilometers north, 4 kilometers east, 3.1 kilometers, 45 degrees north of east. Okay, so let's try to draw the three vectors from the origin. Okay, so notice that the corresponding angles, 2.6 kilometers north is our blue vector, so this is the blue vector towards the north direction, about 2.6 kilometers. The second vector is the green vector, 4 kilometers east, so 4 units towards the east direction. The purple vector is our third vector. It is directed 45 degrees north of east. North of east is on the first quadrant. This one. This is your 45-degree angle as measured from X. Now, the resultant vector is 7.83 kilometers based on the computation. It is directed north of east, therefore it is on the first quadrant. Now, we cannot see directly how we come up with the red vector here. If you're going to draw, you should employ head to tail or the parallelogram two vectors at a time in order to draw determine the resultant vector using graphical method. If we're going to draw the vectors head to tail, try to notice that the green vector was drawn on the first vector. In succession, the third vector is drawn on the tip of the second vector. The resultant vector is the same as though when we draw the vectors from the origin. The resultant vector is the vector again drawn from the tail of the first vector ending up to the head of the last vector. Now, we are given three vectors. In this module, if you're going to click the parallelogram method, you will have this error message that says that the parallelogram method is only used for two vectors at a time. Okay, so let's have a different set of examples. Okay, so for this example, problem number 5, we are given two vectors, but both of these two vectors are on the quadrants, unlike the previous examples wherein there are vectors that are on the axis. So let's try to employ any of the methods here. Probably we could start with the parallelogram method. Okay, so this is actually the examples that I have presented to you a while ago. If we're going to draw this head to tail, try to notice that we end up with the same vector arrow for the resultant vector. If we're going to draw this from the origin, if we're going to draw this using the parallelogram method, and finally, if we're going to show the components of each vector, try to notice that all the details that we have done and we have included in drawing our vectors. Let's try another example. Okay, so let's try to draw the vectors from the origin. Okay, so an error again, an error on scale again. So let's try to adjust the scale. We make use of 1:10. Let's draw the vectors. Okay, so as you can see, these are the drawings of the vectors. If you're going to draw this with using components, showing the components, the corresponding projections are drawn. If you're going to draw this head to tail, notice that we end up with the same vector, resultant vector. And again, we cannot employ the parallelogram method here, since the parallelogram method is used for two vectors at a time only. Okay, so I'm going to present to you 4 problems. I will be flashing them on the screen, and I expect that you will be doing problems number 7, number 8, number 9, and number 10, drawing the vectors using graphical method. I will not be showing to you the graph. I am expecting that you will be doing this, and you will be passing your solution on Monday. Okay, so this is problem number 7. Compute the x and y component of each of the following vectors. Vector A, 12 meters, 37 degrees east of north. Vector B is 15 meters, 40 degrees south of east. Vector C is 6 meters, 60 degrees south of west. So these are the corresponding vector components. And this is the computed resultant vector. I expect that you draw the vectors from the origin. You draw the vectors head to tail. So since you are given 3 vectors only. So you need to show that if you employ the 2 methods using drawing the components accordingly, drawing the vectors from the origin, you would end up with the same resultant vector if you draw the vectors head to tail. Again, this is your problem number 7. I expect that you will be passing this on Monday. That would be on Monday, April 18. Okay, problem number 8. Next is problem number 9. And finally, problem number 10.